Okay, we'll get started. So welcome. So we are here today for the PhD thesis defense of Alex Kurvich. So he's an astronomy PhD student. He came to us from Carnegie Mellon. He had already published a couple papers. So he had a very strong application. And for his PhD, that what I would really characterize as very influential work, he primarily used numerical simulation to study the interplay between star formation and galaxies and feedback from stars. Questions like how is star formation regulated in a galaxy, and also very important recent work on the role of this in the emergence of thin disk galaxies like the Milky Way, which were not present in the early universe. And in addition to this science work, Alex has also been very active in software development. He developed a number of packages we use to render our simulations, including one collaboration with Aaron Geller called Firefly, which is interactive and actually led to a publication that's part of Alex's thesis. As many of you know, Alex has also been extraordinarily active in outreach in Sierra, so we're very thankful for that contribution. And he's received many awards. He was a Blue Waters Fellow, an NSF Fellow. He's also received several prizes for scientific visualization. And fittingly, in a few months, Alex will start as a senior visualization specialist at NASA Goddard. And so the plan for this morning is we'll have roughly a 1 hour of regular open talk. And after that, most of you will vacate the room and we will examine Alex on his understanding of what he wrote in his thesis. And subject to success, watch for your email. I will advertise an opportunity for Wednesday morning champagne. And okay, so we're looking forward to your presentation, Alex.
Well, thank you, Claude-Andre, and thank you everybody for coming to my defense and for the for the people on Zoom as well. I'm really excited to get the opportunity to share with you all just part of what I've been working on these past 7 years here at Sierra. But before I begin, I want to take a moment to recognize the loss of Jose Flores Velasquez, who was a Northwestern RU student that I supervised in the summer of 2017 from Cal Poly Pomona. As many of you may know, his life was tragically taken in 2019, just after he finished his first year of graduate school at the University of California, Irvine. Jose was a very talented astronomer with great potential, and his loss is felt deeply by all of us who knew him for his warm smile and kind heart. Though he was not able to finish his research project, I was very grateful for the opportunity to work with him and for the assistance of our collaboration in completing it and eventually publishing it in order to share his results with the community. It's a great paper with very important results that influenced some of the work that I'm going to show you today. And so while I realize that this is kind of a heavy way of starting with this, at some level, a celebration, I hope that you'll join me in continuing to recognize his ongoing contributions and impact on our field as I talk about my thesis. So I have outlined and structured, good, perfect. I have structured my talk thusly. There are 3 parts corresponding to each of the 3 chapters of my thesis, prefaced by a brief introduction. In part 1, I will describe an analysis of disk galaxies and how star formation rates are regulated in them. In part 2, I will describe the connection between the emergence of galactic disks, their stability, and bursty star formation, in some sense unregulated. And then in part 3, I will describe some of the visualization software tools that I developed that helped enable parts 1 and 2, but also have had a very large impact on our collaboration. And as Claude-Andre mentioned, have led to me getting my next job. So that's maybe the most important part of all. So let's go ahead and hop right in to the introduction. So star formation in galaxies has been observed for the past few decades to follow an empirical relationship called the Kenniket-Schmidt relation, or sometimes the Kenniket-Schmidt law. Now, what the Kenniket-Schmidt relation describes is if you place an aperture over a star-forming disk galaxy, like M51, the whirlpool that I'm picturing here, and you average all of the star formation that's happening, and you compare it to the gas mass content in that same aperture, the two fall along a power law, maybe unsurprisingly, over almost like 4 or 5 decades. So it's really a strong correlation between these two quantities. And now, while the Kenniket-Schmidt relation was originally observed for globally average quantities like this, like a single aperture covering the entire face of the galaxy, it was soon realized that as you look on smaller and smaller scales, that this relationship still held. The same power law was falling out if you compare the star formation rate surface densities and gas mass surface densities that you measured, even just on patches of the galaxy. And so this came to be referred to as the resolved Kenniket-Schmidt relation. So here is that power law. Here on the left, what I want to draw your attention to is this yellow square. So that's M51, what we were just looking at. That's that first aperture. These blue triangles are that second set of smaller patches. And these open circles are going to be the even smaller patches. And if you look at them, you know, these power laws are very similar with the same, basically the same slope and normalization. And with the key caveat that as you're looking on smaller and smaller length scales, there's more and more scatter from this relationship. And that's a point that I want to highlight here because we're going to return to it later. So this power law is parameterized here down at the bottom as the star formation rate surface density, which has units of mass per time, and the gas mass surface density, which has units of mass. So we need as well something with units of time, the free fall time of the gas, and then this dimensionless parameter here, epsilon free fall, which is an efficiency. So what fraction of the gas mass is converted into stars on a free fall time? And so this efficiency sets the normalization of the Kenniket-Schmidt relation and is observed in real galaxies to be somewhere between 1 to 2%. And we can understand that as star formation being very inefficient, because if we allowed all of the gas in a galaxy to just collapse and form stars, it would do so on the dynamical time of the ISM, which is a couple tens of millions of years. Instead, we see that galaxies persist with their gas reservoirs for more than 100 times that duration, more like billions of years. So as a theorist, or as theoreticians, I guess, in general, we want to be able to understand and explain this empirical relationship that we observe in the real universe. And there's a class of models known as equilibrium star formation models that's been very successful at doing so. And here, the idea is that if you model your disk galaxy as just a plane, just a plate of gas in a single phase, gravity is going to want to compress that gas towards the midpoint. It's going to want to fall downwards. Once that gas at the midplane is compressed, it's crushed by the weight of the overlying gas. Eventually, that much denser gas will fragment. It will turn into gravitationally bound clouds, form stars. Those stars will then return energy and momentum into their environment through stellar feedback. So that could be like radiation pressure or stellar winds or even supernovae, which will stir up the gas and drive turbulence, which creates a resistive pressure force to the crushing. And the core fundamental idea of these equilibrium models is that the amount of crushing from the weight of the overlying gas tends to balance precisely the amount of support because there's a a feedback loop between the two, such that you have your galaxy ultimately in a state of hydrostatic balance, akin to what goes on in the interior of stars. And so specifically, this fundamental assumption of this class of models is that P equals W, or that the pressure to weight ratio equals 1. So again, I want to mark this because we're going to come back to this concept later on. Under that assumption, it's actually fairly straightforward to derive the Kennick-Schmidt relation. Here on the left is an expression for what the weight, the crushing force is. Just if you assume, that the gas is in like a plane geometry. And here on the right, if you assume that this pressure, this turbulent pressure is driven only from star formation, then you just have this star formation rate surface density, and then this conversion factor, which is the momentum that's generated per unit star formed, right? So this factor has units of kilometers per second, and is typically something like 1,000 to 2,000 kilometers per second. That's what we understand it to be in these models, and seems to match, what we see in the observations. Now, once you've assumed that P equals W, you can very easily set these two expressions equal to one another. And then we can understand that this relatively low efficiency is really reflecting the relative strength of gravity versus feedback. And in particular, that gravity in general is a very weak force. So once you have expressions that look something like this, you can make plots, like here on the right. So this panel in particular is from Claude André's 2013 paper, where he applied a model like this to gas-rich galaxies, observations of gas-rich galaxies, and was able to demonstrate that these models were successful in predicting both the normalization and the slope. But it kind of begs the question, is this?
I just want to make
what's up, John?
wait till the end for questions.
Okay, the normal similar.
This, I think, is pretty short. So I just wonder if you could give me a flavor of these models, how they reach this 1,000 to 2,000. In other words, just in broad strokes, are these analytic models, or are these like simulations that give a result that you then use?
Yeah, so for the most part, like values of P star over M star come from stellar population synthesis models. And so I think that there's a little bit of numerical simulation in that at some level, but also, some understanding of stellar evolution. Ultimately, the question that you want, like what P star over M star is encapsulating is how much momentum is coming out from radiation pressure, stellar winds, supernovae. And so each of those, you can talk about a Sedov-Taylor, phase of a supernova and the snowplow phase and how much momentum you expect there to be. So it's a combination of both.
I see.
But
Okay.
the specific value of P star over M star, we would take from like Starburst 99, which is a stellar population synthesis model,
Okay,
but
thanks.
they've kind of done all that work. Okay, so these models are at some level almost too good to be true, right? Like how could something so simple, like a galaxy that's exactly a plane, looks like a platter, has only one phase of gas, which we already know is kind of internally inconsistent because there have to be these gravitationally bound clumps, which I haven't talked at all about, is like, how does that mix up things at the center? And so we would like to understand, in a much messier system, could these fundamental assumptions still play a role in regulating the star formation rate inside these sorts of galaxies? And so to answer that question, we turn to numerical simulations, in particular the fire simulations, which are very well suited to answer these sorts of questions for a couple of reasons. Number one, they have a very high resolution and they resolve individual star forming regions. Number two, they have very detailed models for all the relevant stellar feedback processes. And so, as we're self-consistently forming stars with our star formation prescription in these resolved star forming complexes, then we are self-consistently modeling their feedback, and we can compare it to gravity. But perhaps most importantly, these simulations contain galaxies that are disks that fall on the Kennick-Schmidt relation. both the globally average in the globally average sense, but also in the result sense. And so we can expect that somewhere in these simulations is encoded the information about the origin of the Kennecott-Schmidt relation. And so that's what we set out to investigate. And so that's the end of my introduction. At this point, I'm going to go ahead and move on to part one, where we test some of these assumptions in the fire simulations. So here is an image of a disk galaxy from the fire simulations. I don't know if it's possible to like dim the lights in the front. It's not super important. Please don't cast us all into darkness. Beautiful. Thank you, Clark. Much better. So up here in the top panel is the gas content of the galaxy. Here I'm showing an edge-on view of a disk, a very thin disk around redshift 0 in our simulations that is colored by temperature and really demonstrates just how like non-platter-like and non-single phase these galaxies are. So if you look here at this like sort of hazy green gas, this is going to be your diffuse hot gas, that might be from like supernova bubbles that are escaping and driving winds. There's this kind of grayish or light bluish warm gas here that's like the envelope is maybe the meat of the galaxy, where maybe, okay, this is where we expect there to be a lot of turbulent pressure. And then you can see these really bright, dense, blue, cold gas clumps where star formation is actually going to be happening. And then down here on the bottom is just a rendering as if the Hubble Space Telescope were observing our galaxy. So we're modeling what the starlight and the relevant bands would look like, and then applying some gas or dust attenuation.
Real
Yes,
quick
Bill?
question. I apologize if you said this, but are these slices through your simulation? So are these like these temperatures, might they be line of sight average temperatures?
The second, line of sight averaged. Yes, I did not say. Thank you.
Okay, thanks.
So what I have also plotted on top of here, just to give you an idea of just how thin these galaxies are, is what the scale height looks like. And so, one thing that I didn't totally appreciate until I made this particular plot was just how close to the disk 4 scale heights was, because I think we were thinking much further at first. But most importantly, perhaps, is the fact that this disk flares at the edges. And so we thought maybe this would be important and that we needed to account for it. So to answer this question about whether these fundamental assumptions in equilibrium star formation models are actually satisfied in the simulations, we set out to measure the weight of the overlying gas and the turbulent pressure in patches across the face of the disk. But we quickly found that if we only included the turbulent pressure, we were not there was energy missing. There was something missing. But it was maybe not so much a surprise that especially in the hot gas, it turned out that the thermal pressure was very important in addition to any kind of turbulent pressure. But even still, we were finding that the two weren't matching. But it turns out that we had to relax an assumption about our model. So already we were learning something, is that if we included a bulk flow term and relaxed the assumption that things were hydrostatic, but that you could have a steady state fountain flow that's time steady as stuff is moving out from like the center and then back down at larger radii and then being radially transported, that can provide a measure of vertical support as well. And then once we've included all 3 of these terms into the total pressure, we were able to find, as I'll show momentarily, that our galaxies maybe were not in hydrostatic balance, but that they were in a state of vertical pressure balance instead, which was the term we decided to come up with. Another term that's sometimes been used when talking about these bulk flows is like a dynamical equilibrium, other than a hydrostatic equilibrium. And so when we plot these patches versus each other, so here on the left, I'm plotting the weight. Of course, thank you. Here on the left, I'm plotting the weight. We're back. The weight versus the pressure. And here is just the P tote equals W 1-to-1 line. We can see that the majority of the points, you know, they are falling along this relationship. So these contours they contain 50% of the points and then 90% of the points, but there's actually a significant amount of scatter. Analogously, if we compare the pressure to the star formation rate that the star formation rate that we measure and the pressure that we measure, and then compare that to you know, what we would predict based off of this simple scaling of P equals sigma SFR times P star over M star, we get a value of P over M star that shoots through them. We were able to fit for one that's about 1,000 kilometers per second. So that's in line with these models that we expected them to be.
Sorry, one other really quick question. The P total you're plotting here, does that include the fountain effect as well?
Yes, very importantly, that if this P total includes all three terms.
So it looks like there's a lot of the materials to the bottom right, and there's less to the upper left. Looking at that left plot.
Here, down
I see
here.
more stuff to the bottom right than to the top left, but maybe because it's a log plot, that's just, it's still the case that the best, that the line is still the best fit. Is that right?
Yes, no, for sure. I think the question just is what's going on in this region where there's not a lot of pressure, but there is still weight. And I will show you what those regions look like.
Great.
That's actually a great segue because I think that's the next slide. It is. So we wanted to understand, you know, where was this scatter coming from? There was like some weird little corners where things weren't exactly looking like we expected. And so then we took these patches and we made a map of what the pressure to weight ratio in each of these patches look like for 4 different length scales. So what I was showing you on the last plot was the 1 kpc length scale, but we made similar plots with similar you know, outcomes for all 4 going down to 100 parsecs. And where that region that you pointed out in particular, Giles, was here in between the region between spiral arms where there's a void. So you don't have a lot of gas, but you still have like a very smooth stellar potential. And so there, the gas self-gravity is not super important, though maybe on average, it could be, you know, a modest contributing factor. So because you have so little diffuse gas, but still this large stellar potential, your weight ends up just kind of getting thrown off compared to the amount of pressure that's actually there. Likewise, so that's happening up here in the top right corner. In the top left corner, you have something that's over pressurized. So it's living up here in the top of the color bar. So P is much larger than W because there's been an active star formation event with a lot of overlapping supernovae that are actually driving one of these winds outward. So we quickly realized that, you know, okay, maybe in a globally average sense, if you're looking over the face of the disk, our galaxies are in a state of vertical pressure balance, but clearly there are some non-axisymmetries that are playing a role in driving some of this scatter. And in particular, it seemed like these spiral arms were important. So to try and measure, you know, how these non-axisymmetries played a role in the scatter, we plot a set of concentric rings down, and we wanted to measure what the standard deviation of the pressure to weight ratio was in these rings, just to quantify how much the non-axisymmetries were important. And so that's what's happening here on this plot. So as a function of radius on the x-axis, here is the scatter in the pressure to weight ratio. And what I want to draw your attention to is as you're moving to larger radii, you're having more deviation within a ring. And as you look at smaller and smaller patch sizes, you also see more scatter. Now, hopefully this reminds you of something that I had demarcated before. And now it's this same sort of scatter is analogous to when we were looking at smaller and smaller length scales in the Kennedy-Schmidt relation. And so, when I was first looking at this, I was actually quite surprised. And then so I tried to eyeball, just how much scatter we were talking about on each length scale. So here, just as an order of magnitude, looking at these blue points, I called it something like half a dex of scatter in vertical scatter for the 2 kiloparsec data, the observations. And then if we plotted that half a dex here on the left, then we could compare it to what we were measuring for the 3 and 1 kiloparsec patches. We found that, depending on what radius you're looking at, it's falling kind of like right in between, right at the same level. Analogously, if you look at the smaller 500 parsec observational data, then we're landing somewhere closer to a dex where our 100 and 300 parsec measured values from the simulation are starting to top out. And so it seems like there's some kind of link between deviation from a pressure to weight ratio of 1 and scatter in the Kennedy-Schmidt relation. So at first I was like, oh my gosh, this is incredible. But then I realized is that if you go back and you relax this assumption that P equals W exactly, and you leave it as a variable in your derivation, then it ends up appearing as P over W here. And then if you just do a simple propagation of error, you can see that scatter in this quantity is going to directly correspond to scatter in this other quantity, which had not been something that had really been articulated in the literature until we came along. So that was very exciting. So with that, that's all that I had time to talk about from my first chapter. I hardly scratched the surface of this in the sense that, I've shown you a whole bunch of quantities that were averaged over all of the gas phases. We went in, dove in, looked at individual gas phases, how different pressure terms play different roles, and different gas phases at different heights. But unfortunately, have a lot to cover from 7 years. So instead, I will just summarize, some of the results here that I've shared. Is that first, what we found is that ultimately the basic assumptions really are satisfied in the fire simulations, but with some hugely important caveats. First of all, maybe not hydrostatic balance, but more like a vertical pressure balance where you're allowing for the steady state fountain flow. And second, that the scatter from a ratio of pressure to weight ratio of 1 is linked to scatter in the result of Kennedy-Schmidt relation. So that these two fundamental assumptions are on average true, but start to get at the heart of why the resolved Kennedy-Schmidt relation has the scatter that it does. So yeah, I guess, I don't know, am I supposed to ask for questions before I continue, or? Yeah, I'm just gonna continue.
I was just asking when they occur to you.
Yeah, no, that's fine, John. Keep asking. So moving on to part 2. So in part 1, I focused on the analysis of a very happy, very stable thin disk, where we could talk about star formation that was well regulated, and we knew kind of what was going on, and we just wanted to test some assumptions. In part 2, I'm going to kind of venture out into the Wild West and instead look at galaxies that are much less clean, much messier, and are in some sense not regulating their star formation rates and have not formed disks. So here's a movie of the fire simulations during this time period. I like to look at this middle panel here, but you can look here on the left if you're more interested in the gas, or you could look more here on the right if you're more interested in the star formation, where the young stars are being formed. And what I hope that you're seeing is that the galaxy is certainly not a disk. It's more like a spheroid that's exploding, throwing chunks of itself out into the air. But then eventually you're starting to see some net rotation, like there's some kind of disk structure happening, but then it's like burping and disrupting itself through violent feedback episodes until right here at the end, it decides, okay, one last final hurrah. And now I'm going to settle down and be a happy little disk and evolve quiescently all the way down to redshift 0. So,
That's the question. So is this the time over which you make this average to vary the weight to the pressure?
no, this is totally
So
separate.
when you are making those, comparisons.
So back to part 1.
Yeah. It's a much calmer state.
Yes.
Okay.
Yeah, and for that, it's just the last 600 million years, like Z equals 0, 600 million years back. This is like 6 gigayears before then, before the disk has actually settled.
Well, so, but in the plot you showed from Padre, the gas-rich galaxies that reaches 1 to 3 also fell on the same kind of enrichment relation. So
Yes.
if you perform the same analysis in part 1 on earlier galaxies, how do you interpret that then?
I will cover something similar. So we performed an analogous, we performed an analogous analysis that, gets at the heart of whether there's some kind of equilibrium and whether star formation is regulated. To the answer to that question, I will say is that's why I'm being hesitant when I say that the star formation rate isn't necessarily unregulated, it's bursty. But on a long enough time average, then it actually does not change much between the 2 phases. And I don't have a good plot that shows that because I divide by that average on everything to emphasize the burstiness, but it's not there. We'll get there. It's an excellent question. So this I showed you something from a simulation. That's great. But I want to try and tie this into something that occurs in the real universe. So here on the left are just little thumbnail images of low mass and high redshift galaxies. And as you can see, they're much clumpier. So they have these distinctive UV bright clumps in them, and they have much more irregular morphologies in these bands. Versus if you look in the local universe at much lower redshift or at much more massive galaxies, you'll see instead these beautiful grand design spirals. And there's some understanding that galaxies here in this phase at early times when they're dispersion dominated undergo a process known as disk settling, where they will transition from one phase where they're dispersion dominated to the other phase where they're more rotation dominated. And that's sometimes referred to as the epoch of disk settling, and was generally understood to occur around redshift 1 on average. But I think, Claude Andre was mentioning before we started, this is really a hot topic of research at the moment. And it's starting to seem like, I won't have any time to cover this, but I just, I have to plug it. That maybe there's not a single epoch of disk settling, but rather individual galaxies can settle at different times depending on their growth histories and depending on their growth histories. That's all I'll say there. So, okay. So we have this idea of disk settling, and we want to go into the fire simulations and understand what is the relationship between disk settling, star formation rate, the regulation, and then if we can tie the 2 together. So here on the left, is a galaxy before its disk has settled. And then here on the right is just, I think it's 2 gigayears later after the disk has settled. And what I want to emphasize is that both of these images are taken so-called edge on. So this is not like one that's edge on the right and then face on the left, which is like a common misconception. Instead, we're looking at something that has some kind of net angular momentum on the left that we've aligned as our edge for this image, but does not have the same kind of disk structure that you can really clearly see. Here, these images, again, are color-coded by the temperature, and you can very clearly see this complex, stringy, cold gas disk on the right, and more clumpy, gross, finer, spherical-looking, messy thing on the left. And so again, we have this expectation that, okay, this physical phenomenon is happening. We trust a lot of the physics going on. Somewhere embedded in here must be some kind of information about the process of disk settling. So to try and get at the heart of that, what I did is I quantified now in spherical shells what the breakdown of energy is. We couldn't take the exact pipeline that we applied at low redshift because that assumed that things were like on a platter or had some like perturbation on a platter. Whereas this, clearly has some kind of spherical geometry. So we picked something that was going to work in both cases. And what we did is we took the kinetic energy and broke it up into its different coordinate components. And then the thermal energy, we measured alongside that. And so I find it easier to describe what we expect to see by starting down here on the bottom. Under this analysis, if we look as a function of radius here on a log scale, there's a clear bifurcation where there's an outer region that is dominated by thermal energy, supported by thermal pressure, doing its whole thermal thing. And then you get down the lower, smaller radii closer to the center. And instead, you're rotation dominated and everything else has really dropped down to zero. Contrast that with the before times when in this inner region, everything is like a mishmash partitioned equally between the different components and the thermal energy. And even if you look in the outer region, clearly there's some thermal dominance, but it's not quite as strong. And it's definitely like more gradual as it's building up. So for the sake of time, I will only be focusing on my results that focus here. And what I'm going to define as the ISM within 5% of virial radius. But in the corresponding paper, we spend some time as well talking about what's going on here in this outer region of the CGM. So here's where I want to try and define what I mean about whether star formation is regulated or not. Here on the left, so in this left plot, what I'm showing is as a function of time, what is the star formation rate after it's been normalized by the running average. And so here, I hope you can see that the star formation rate is very fuzzy. It's changing by like an order of magnitude very quickly. And then there's some moment where it decides, no, I want to get my act together. I'm going to find a specific value of the star formation rate that I'm going to, be nailed to, and I'm going to happily evolve quiescently. And it may be hard to see, but there's a faint gray line here that separates these two regions between bursty and steady, or as you might see here, down at T bursty, T minus T bursty is 0. And so we define T bursty by looking at, I don't actually know how to get rid of that red swipe. It's,
There it goes.
I think I colored it black, so. It was too quick to come back to the laser pointer. Anyway, we measure the scatter, the running scatter, and what we see is that in this bursty phase, the scatter has like some, on average, constant amount of scatter, something like 0.3 dex, though of course it definitely gets higher. Again, this y-axis is a log scale. And then there's some moment where it just plummets by like an order of magnitude, and it gets down to a value of like 20%. And so it really does, there's this qualitative shift in the way that the star formation rate is evolving over time. And so what we can look at now that we've defined this T bursty is how the energy, which I showed on the last slide, is divided between each of the different components. And so in particular, if we just look at the fraction of the energy that's in rotation, we can see two qualitative phases. So here I'm stacking the results for 3 different simulations. and offsetting them by their independent T bursties. And you can see that when we do that, that they're pretty self-similar and they tend to overlap. And if we're looking at this early phase, what we see is that, the fraction of energy concentrated in rotation is something like, a quarter to a third, corresponding to this equal partition between the coordinate directions and the thermal pressure. Then at late times, instead, this value jumps up very, very close to 1 with this very rapid transition between the two. So that's if we take a look at the fraction of energy and how it's divided. If we look instead at the normalization of the energy compared to the gravitational binding energy, we see again 2 qualitative regions. So at late times, when you have like a happy steady disk, this ratio of the total energy to the gravitational binding energy is something like a half. So this is what we would expect from the virial theorem. So we're very happy about this. But if you go back again in the before times, we see a totally different story. Instead, the galaxy is what I like to call like doubly out of equilibrium, in the sense that its total energy is much more than the gravitational binding energy, but it's also fluctuating very rapidly, right? And so in this sense, the total energy within the galaxy is not being balanced by gravity. But so that was for 3 simulations. If we instead zoom in on just 1 simulation and now break it up by phase of gas with the temperature cuts denoted up here, this white, if I swipe too fast on my phone, it doesn't like that. Okay, this white line here, I actually just showed you that on the previous plot. We were looking at that. That was for the total amount of gas. I think it was orange on the last plot. So, okay, this is what we were looking at. But if we look at the cold and the warm phases, there's actually this middle regime where instead of being totally out of equilibrium, or even just like a little bit in terms of its magnitude, you just have these rapid fluctuations about equilibrium. And so there's actually not just 2 phases, but 3 phases, where in the first we have what I term fireworks, because they're like exploding and they kind of look like fireworks. In this middle, we have this protodisk phase where it is trying to form a disk, but it's being disrupted by feedback. And then at late times, we have the phase where it's able to stably form a thin disk. Now this in particular is very interesting because just, I don't know, the day after I posted this paper to the archive, there was one of these papers, and then in the following like 2 weeks, there was another 2 that were enabled by new results from Gaia DR3, where we were looking at previously unobserved populations of very old stars in the Milky Way, where they were finding a very similar 3-phase structure that was analogous. In particular, they were finding that the oldest, most metal-poor stars in the stellar halo seem to be on these very dispersion-like orbits without a net angular momentum amongst them. Then there was a rapid transition to what they're calling a thick disk, as identified by some chemical tagging process that's common in galactic archaeology. I'm not going to go into that, but they call it the thick disk. But what's most important is that kinematically, it has some kind of net rotation, but not as much as what the eventual thin disk will have. And then again, there's this kind of rapid transition between the thick and thin disk, though they seem to find that this corresponds to a particular merger, and the exact timing and duration of these phases is a little bit different. So obviously our simulations aren't a perfect analog of the Milky Way, but it was really exciting to see that they were seeing kind of the same 3-phase structure.
Alex, could you say what the vertical axis is on the right? Because I don't think it's the same as the one on the.
Oh, it's definitely not. Yes. So I'm not, the vertical axis on the right is actually, I think, a star formation efficiency, but it's not important for like what I could just as easily have had a timeline. But yeah, that's why I covered it up. Okay, so that's all that I have time to talk about here for part two. So just to summarize, first, what we found in the fire sim, oh yeah.
No. Well, so for the Milky Way, this transition between phase 2 and phase 3 seems to correlate potentially with this last major merger.
Yeah.
This is presumably something that you could investigate with fire. Do you see any evidence of mergers playing a role in this transition?
So that's not something that like I had the time to look at, is like on my list of things to do, like as a postdoc. Somebody will do it eventually, I imagine. Just from the movies, you don't see like something fly in and disturb stuff. So I've always said like, yeah, I don't think we need mergers, but I don't know. I mean, Chitzka, I remember when we were here, like you were teaching me how to look at the merger trees.
Future investigation.
Somebody will do it in the future. Anyway, moving on. Oh, I'm sorry.
So, are you about to go to the visualization phase?
Yes.
Yes, so I had a couple of questions about the
Absolutely.
second phase.
Yeah.
So one of them was, I want to make sure I understand what the situation, so T bursty is like the duration of this burst before it.
T bursty is the moment in like cosmic time when the galaxy ends bursty star formation.
Okay.
So that's what T minus T bursty means,
get
that at 0, this is when the scatter drops.
Okay,
And so what you see is the rotation pick up correspondingly at T bursty.
great. Okay, that's clear. The question I had, well, my first question then is, I think you said before T bursty, there was not a balance between the gravity and the other components.
Yes,
And
and we can see that here on the right.
so my question is, in a situation like that, where I think of this as a system that's not balanced. Maybe I'm missing something, but wouldn't it just sort of fall apart? And
Yes, so I have it kind of like grayed out here on the right. What it comes down to is being able to break it down into phases. So the vast majority of the energy in this pre-settled phase is in the hot gas. And so that's what we're plotting, is the energy fraction. But only a very small amount of mass is in the hot gas.
I see.
And so what's happening is that a lot of this energy is bent in very energy loaded winds. And if I had not grayed that out, you'd see that it's like off the charts, literally off the charts.
So there's stuff being expelled.
Yes,
Okay,
stuff is being
great.
expelled, but it's a small fraction of the mass.
Got it. No,
And the
that's-
cold, and you see that the cold and the warm stuff still is getting expelled, but not nearly as much as the hot gas. Like if I showed, I
Right,
shouldn't have
right,
grayed it out, but I didn't.
Yeah, no, that makes perfect sense. So my second question then is just kind of informational. When you do okay, let me back up a little bit. You said there was some controversy as far as when this transition to a disk-like structure happens. You said it was around Z = 1, but it's not known.
Oh, sorry, the epic of disk cells.
Right.
Yeah.
So I wonder if when you do your simulations, I assume it's the case, but I don't know. Do you need to assume a Z? So you don't, okay.
No. So I'm just looking at when these galaxies self-consistently, as we're modeling their star formation rates, decide to stop being bursty. It just so happens, that coincides with when the disk forms. And so we think that this is really important. So to have a time steady star formation rate, you need a disk. And so this is really just even more support for these like disk equilibrium models in the end of the day.
So your simulations could apply to a Z of 2.5 or
2.5.
a Z of 1 or a Z of
Exactly.
0.5?
It just depends. So our initial conditions start from statistic like density perturbations taken from statistics just after the Big Bang. And we simulate all the way down to Z = 0. So these aren't idealized simulations that we just pick a Z and then go forth. These are self-consistently grown galaxies coming out of a cosmological context with cosmological accretion, their own satellites, winds that they generate. That was something that I had on my fire.
So that means in principle, you can tag each of your simulations with a Z
Yes,
because they're taken from a grander scheme.
I could plot like T bursty, does this
Okay.
happen? And make like here's the distribution of Z's.
So does that
when
mean you
happens.
could, with the kind of work you're doing, ultimately tell people when you think this transition happened? Did it happen
Yes.
as equals 1 or 2? Or-
Yes, yeah, like in the Milky Way. Yes, so I helped Anna Yu and Anna Perul do just that. And our simulations predict that the Milky Way formed. Well, I guess the observers can do that as well, because they know what the age of the stars that start to have the spin up
Right.
are. If we apply our methodology to their same kind of data, we tend to find that our fire galaxies settle a little too late compared to similar disky galaxies. But again, this is the sort of thing that like
Yeah.
we had intended to do, but
No, it's very
It's
interesting. Yeah. Thank you.
Yeah.
You might be getting at this, but sort of a chicken and the egg question. Does it stop being bursty because it formed a disk, or does it form a disk because it stopped being bursty?
so this was something that we struggled with for a really long time until I think we did get to the bottom of it. And so in a totally separate Mammoth manifesto that Bill Hopkins put together, who's like our code guru, and runs all the simulations in our collaboration. He did a bunch of idealized tests where he was able to force a disk to form, force bursty star formation to end, and then see like, oh, which one triggers the other, whatever. And it turns out that there's actually 2 independent triggers that happen to coincide just because cosmological growth is such that you get the depth of the potential right and the shape of the potential right at about the same moment in time. But yeah, that's definitely not covered here. Any other questions before I move on to the visualization stuff? Great. All right, part 3. So in just this talk, I have shown a lot of visualization. And I hope that they have helped convey a lot of the points that I'm trying to make. And so I will assert that good visualizations are really crucial to communicating complex scientific points. But it's really hard to make really good visualizations for at least, though there are more, at least 2 reasons. Number one, these visualizations in particular are very computationally expensive. So to actually project through them, and especially for the movie, to do so to make so many frames and then squish them together into a movie that runs for 2 minutes takes a lot of effort. So that's reason number 1. Reason number 2, it's difficult because you're investing all that computer time, but you don't necessarily know what the simulation looks like. You don't know what angle you want to put your camera at. You don't know what color scheme you want to use. And so in principle, you would like to rapidly iterate and find what the best parameters for your visualization are to convey your point the easiest. But because of the computational expense of making some of these images, that's not really possible. You kind of just have your setup pipeline and you run it, and you kind of hope it looks good, and it looks good enough. So to address the first concern about computational costs, I created Fire Studio, which is a combination of Python and C library for creating these renderings. It has a lot of built-in tools that allow you to easily interpolate between frames and stitch them together to make movies. It has some kind of cookie cutter recipes so that you can plot, say, streamlines on top of your images, or you can make these Mark Hubble images. All of this stuff, all connected to the same interface that I spent a lot of time optimizing, parallelizing, and making just really easy and convenient to run, because, you know, it was important to me that everybody in the collaboration have the ability to make these sorts of images, rather than constantly having to go to like one of Phil's papers and like take a screenshot or like steal the figure, you know, if they knew better, from the archive source. Is that they should be able to feel a level of ownership. So that solves, you know, the first problem, and Fire Studio ultimately has given me a lot of work in terms of supporting people in the collaboration as they've tried to use it, which has been interesting and educating for me. But it doesn't really solve the second problem, which is that we would like to rapidly iterate and explore our data before committing to this, you know, very heavy explanatory visualization. So to address that second concern, I teamed up with our very own Aaron Geller here in the department, who taught me everything I know. And we created Firefly, which is a browser-based interactive 3D visualization software that allows you to create very easily create simple visualizations that let you, you know, customize the color maps, apply different filters onto the data, you know, toggle different data layers, do all sorts of different things, all within the comfort of a web browser, you know. And with a tool like this, you know, we envisioned scientists being able to load in their data, fiddle around with it, export the settings, and then just feed it in to whatever pipeline they wanted to use and make their happy visualizations. Or maybe if they just like Firefly enough, they can just share those. At least, I think at least 2 papers that Zach has written have had Firefly images in them. So I don't know, I guess it makes publication quality images as well. So I just want to try and highlight a couple of the key features of Firefly. So firstly, Firefly is accessible. It runs natively in a web browser without any installation. If you just go to the URL, it will open. You can immediately jump into it. It makes it great for outreach, or if you want to share results with a colleague, you just have to send them a URL. It doesn't have to be like a 50 megabyte, you know, MP3 that you have to host on Google Drive and then give them access to or something. So that makes it extremely accessible in that sense. It's flexible in the sense that it supports any 3D data. I like to say, if you can open it into a NumPy array, you can put it into Firefly. It's that simple. But also, Firefly supports a number of different visualization options, including 3D scatter plots, so just like points floating in space, 3D quiver plots. So here I'm just highlighting the little arrows that are showing velocity vectors, or even it'll do live projection, 2D histograms as you spin your stuff around, pan, zoom, filter, all of the things that I was talking about before. Firefly is customizable in the sense that you can very easily change the elements of the user interface. You might be overwhelmed by the number of checkboxes and sliders and etc. But every single element here on this UI, I work very hard to address every single one of them so that you can toggle, you can disable or enable them so that you can create custom versions for different audiences. Say you only want your colleague to be able to turn off individual data layers and you don't want to confuse them with all of the other stuff, or trying to make something for outreach for kids and you just want to turn off the UI altogether, or anywhere in between. You can do that without having to change any of the code. Firefly is performant. So it runs client side. It's using your computer's graphics card, CPU, and RAM. So we had to be very cognizant of that and try and optimize it as best we could. I think we did a pretty good job because what our main limiting factor is actually software related, is how much RAM that Chrome and modern web browsers will allow you to allocate to a single tab. So people like to joke that Chrome eats up a lot of RAM. I wish it would eat up more. Because then we could do even more cool stuff with Firefly. But even still, once we've loaded in tens of millions of points, we can get, we've done performance testing, automated performance testing, and shown that we can get interactive frame rates above 30 frames per second for huge numbers, which I'm really proud of. And lastly, Firefly is user-friendly. So it's very easy for users to create their own Firefly visualizations. We put together this excellent Python front end that allows you to, in just like 1 or 2 lines, take your data from its NumPy arrays, put it into a Firefly format, press a button, and then immediately have a Firefly session in front of you so that you can explore it. So here are just some examples of how we've used Firefly for different astronomical data sets. So here in the top are 2 different fire data sets. One, I'm showing the quiver plot functionality just to highlight some stellar feedback driven biconical outflows that are from hot gas that are exiting the galaxy. Here I'm showing off the 2D histogram function in a spiral galaxy to emphasize the flocculent spiral structure. Down here is actually observational data from the SDSS Galaxy Catalog, colored by what citizen scientists have classified their morphology to be from Galaxy Zoo, just a 3D scatter plot. And then down here, last but certainly not least, is a 3D scatter plot of every single star from Gaia DR3 that we could find, colored by their BP minus RP band colors. And so if you look closely, this is the plane of the Milky Way. It's real observational data. This is the plane of the Milky Way, and this reddening is actually dust reddening from dust in the plane of the galaxy. And I said that we could only load maybe tens of millions of stars due to RAM limitations, but now I'm claiming that we put in, you know, like a billion and a half stars into the Firefly. And so to do that, I had to write from scratch a completely new rendering algorithm that progressively loaded data from disk so that it would only find the tens of millions of points closest to the camera as you're moving without any interaction from the user, discarding the data that you no longer needed and loading the data that was inside the camera field of view. And to do that fast enough that you could actually have an interactive experience. And it works really great, I think. Yeah.
Can you comment on what the striping is in the bottom?
It's the scanning law of Gaia, actually. So there's a little bit of overlap as it's moving, and so you get extra exposure on that overlap.
Cool, thanks.
But yeah, we were real worried about that for a while. And then I talked to somebody that's Gaia. She's like, "Oh my God, you could see the scanning law," and I was like, "Okay, all right, we're good. I didn't make a mistake." Anyway, but as far as we know, this is actually the only way to interactively visualize the entire Gaia DR3 data set is with our progressive rendering engine in Firefly. And so I'm really excited about that. And it turns out, actually, I think the AAS journals are excited about that because we just got this email to like sit down with them and do like a little interview thing for the web series. So yeah, I think Firefly is a really great tool that has a lot of promise for people to use it. And so you should consider using it. So those were some static images. Firefly also has the ability to export animations. So here I'm using the built-in tool that within Firefly to just create GIFs of me just kind of panning back and forth. These are 2 snapshots before and after disk settling, that I used for a different talk. Just to emphasize, the spherical structure, clumpy, stringy nature of the cold gas on the left and the happy little new disk on the right. But there's a ton of different features that I'm just not going to have the time to cover. So there are just 3 I want to highlight. One that I really like is the ability to evolve your data in time by extrapolating the positions of each of your points along their velocity vectors. So what that'll do is, of course, eventually that will stop, being realistic because your velocity vectors, you expect them to change as like the particles interact with each other or whatever. But you can really see these streams as they're flowing and converging And it gives you a nice sense of the motion that I just think is super cool. And, you know, we have some cool ideas of how you could load in time series data and let it interpolate, and you could actually have like a movie that you spin around and do all the Firefly things sometime in the future. There's actually already VR support. So the idea there is that you visit a URL on your phone, you slap it into a Google Cardboard, you strap it to your face, and then we have a gyroscope control that allows you to look around your data from a fixed position and inspect it. You know, which I think is really cool. And I think, you know, if we keep building on that and allow, you know, people to like walk around their data and really see it from all different sorts of angles, could lead both to like really exciting outreach experiences, but also like really cool ways of learning more about your data and literally looking at it from the perspective. And then lastly, one that like, I don't know, I'm maybe most excited about, like I remember when Aaron first figured this out, you can embed a Firefly instance within a Jupyter notebook. So if you're like me and you use Jupyter notebooks to do like the vast majority of your analysis, you can in situ with all of your code, load in your data, press a button, and then immediately have like a little pane appear with Firefly that you spin around, explore, filter, do whatever you need. And I think it's just this week, Aaron is working on a feature to export that subset of data that you now selected back into Python so that you can continue doing analysis on it, all in one streamlined interactive workflow. So just to finish up, you know, we have a gallery of some examples that you can find on our website at fireflyviz.com. And I worked very hard on this documentation. There's narrative documentation, API reference, tutorial notebooks. I even recorded myself going through some of them. There's like 5 or 6 videos on YouTube. And of course, you know, from our GitHub repository, you can always like ask a question or whatever. Again, this, you can find it on fireflyviz.com. And so, yeah, I invite everyone here to try it, to evangelize about it, and you know, use it, because I think that it really is going to be a really cool tool. It's going to allow a lot of people to do a lot of interesting things. So you can do that by either pip installing it. You can download the source code from our GitHub repository, which is again linked on our website. And if you are familiar with YT and use it, we're actually already hooked into there. You just take your data region, you press, you know, region.export to Firefly, and then boom, it just works. And so with that, that is really all that I wanted to say today as part of my thesis defense. To summarize, in part 1, I showed you how we found that the assumptions of equilibrium star formation models are mostly satisfied, with some possible, you know, some important rather caveats and some possible sources of scatter in Kinetic manipulations. So some 2 really interesting things that came out of that study. In part 2, I showed you how galactic disk emergence and stability is linked to the end of bursty star formation, and that the transition between these 2 states is very rapid, both you know, new novel pieces of information. And in part 3, I showed you all about Firefly and tried to emphasize the importance of interactive visualization in helping you build very good explanatory visualizations and the importance therein of those. And so with that, I will call it Stars in the Balance and be happy to take any questions.
Okay, thank you for this very nice and beautiful presentation. So are there questions from the audience of the talk?
You mentioned future plans for Firefly.
Yeah.
So you're going to keep developing it?
That's the hope, yeah. Especially, you know, starting a job in Goddard doing scientific visualization. So yeah, we'll see.
Aaron is also still here.
But yeah, Aaron is still here. Yes.
Is the full Gaia data set available online somewhere too? Like,
Yes, yeah, so we used, I think Astro Query to like do a SQL command that downloads it all. It's hosted on the, I don't know, I guess ESA's servers or something, I don't know. We have it here at Sierra. I had Jeff Andrews download it and put it on Quest, but I don't know if that ever happened.
What's the size of that?
It's actually not that bad. The data that we use is 500 gigabytes. I think the full data set is close to like 1.5 terabytes or 2. But that might just be like a subset of the column. So I don't totally remember.
Natasha?
So, am I correctly understanding that basically the limiting factor for what you can visualize in Firefly is just how much data you can load onto your laptop?
Yes, and it's not even necessarily how much data you can load onto your laptop because, I can have my 64 gigabytes of RAM in my gaming computer back at home, but Chrome will only let you use 2 gigabytes of RAM per tab because Google's like, who's gonna need more than 2 gigabytes per tab? Like, clearly that's a memory leak. Like, your developer should fix that. We've tried using Opera GX, which is like a gamer's browser that supposedly lets you unlock and like use more memory, but then its memory meter was telling me that I was using like negative 300 megabytes of RAM. And I'm like, this is fake. Like, you don't know what you're talking about. This browser is a scam. So I uninstalled it. So we were thinking about actually building our own browser in Electron as a possibility, and then just not having that. But then you would need to install something, which is not impossible. Like, that's fine, but it kind of defeats the purpose.
But Firefox.
Firefox has the same limit. Yeah, it's just a limit of modern web browsers. It's like a standard. People just expect that your application should not take more than 2 gigabytes, which is like fair because if I'm like visiting Expedia, it's like I don't want it to take more than 2 gigabytes of my RAM. And the idea of using these very heavy computational, applications on the web just hasn't really hit the like public mindset yet, I think. And so what I kind of hope is eventually the case here in science is that we can kind of lead that charge and say that like these web technologies are really powerful. You can get, in WebAssembly, you can get C-level speed within the browser and with interfaces that you've written in CSS and HTML. And you can build these really amazing applications that then anybody can access, maybe even use as like a science gateway to launch jobs from and like really revolutionize the way that we do high performance computing. If only Google would let us.
Okay, any final questions from the audience? Jessica?
All right, it's more of a comment than a question, but on the last point, I do know one other group that, because of Gaia, started to develop a way to interactively work with like those amounts of data. They've actually, the people developing it actually started a data science company doing that.
Oh, cool.
Completely focused on that. But yeah, it also started out to be able to work with Gaia data.
Yeah.
And so they have this whole tool that, like they say, is useful to do data science starting from like 100 gigabytes of data.
Yeah, and I think especially,
multiple terabytes.
yeah, and I think that, as, LSST, brings us all of this data as well, like, this is gonna be a problem, that we're gonna have.
Yeah.
And it's like, it's one thing to like plot, 0.01% of the data in the tools that we have, but we're really gonna have to develop new tools and totally new algorithms
And so I think
for even just visualizing it.
I think they have a similar rendering, a similar method of like trying to find the part of the data that you're actually looking at and actually using very similar to what you.
Very cool.
And yeah, great. I'm happy to take it in touch.
Sure.
Yeah, I think that would be good. Okay, thank you, Alex. So the committee will stay in this room to ask more questions and look again for your email for advertisements of champagne opportunity, probably in the Sierra Cafe this morning. wish Alex good luck for the next project.
Thank you, everybody, on Zoom. I appreciate, all of you who tuned in,
Okay.
but I have to close things down.